So first of all, I define integers, though everyone knows what an integer is. It's this set. And I also define rational numbers. So what is a rational number? It's just the quotient of two integers. And of course, the one you divide by must be non-zero, as you know well. So the set of rational numbers is a field. So it means basically that inside Q, you can add, subtract, multiply, and divide, and you stay inside the set Q. Okay. Whereas Z is not a field. It's just a ring because you lack division. If you divide 1 by 2, you go outside Z. In fact, Z is an integral domain and Q is its field of fraction. In any case, in order to define what an algebraic number is, first of all, you need to define what an algebraic equation is. So for me, an algebraic equation is a polynomial equation of the following form. So it's a polynomial equation where the coefficients AI are required to live in Z. And you want this first one to be non-zero, and you want n to be at least equal to 1, okay? So this is an algebraic equation. And they have been studied for a very long time. Yeah, sorry, yeah. So let me give you some examples of quite well-known algebraic equations. So this is a very obvious algebraic equation with the B and A integers and B non-zero. This is also a well-known one. This is a very famous one. This is a cubic algebraic equation. And this one is somehow different from the other ones. Yeah, whenever someone enters the room, it sends me a message. I don't know why. So, which prevents me to move to the next slide. Let me try to put this here, maybe. Okay. And so now I can define what an algebraic number is. So what's an algebraic number? It's a solution inside the field of complex numbers, so in C, of some algebraic equation. Okay, so that's an algebraic number. Because C has the property to be an algebraically closed field. So inside C, any equation of degree at least 1 has at least one solution. In fact, an equation of degree n, you count its solutions with multiplicity, inside C will have n solution exactly. And so I denote by Q bar the set of algebraic numbers. So an algebraic number is a solution, complex solution of an algebraic equation, and the set of algebraic numbers I denote by Q bar. Q bar turns out, in fact, for those who know a little more, to be the algebraic closure of Q. So the first remark is that Q is contained in Q bar. So why is this? It's because of this first equation here. The solution of bx minus a is a over b. So every rational number is the solution of an algebraic equation because b and a are integers. So let me give some examples of algebraic numbers which are not rational numbers, because now we know that rational numbers are all algebraic. So square root of 2 is the solution of this equation here. I, the famous solution of this equation there, one of the two solutions. J, solution of this one. This one, as I said, I don't talk about yet. But there are numbers which are not algebraic also. And so, because in fact, the set of algebraic numbers is countable. And so C is not. So there are obviously numbers which are not algebraic, but to give precisely one of them is a difficult task, very difficult task. And so, for example, the number pi is not algebraic. And there's a branch of number theory which studies those numbers which are called transcendental, which I don't know anything about, but it's hard to produce this type of example explicitly. Okay, so let's go back to algebraic numbers. So the set of algebraic numbers Q bar is also a field. As I said, it is in fact the algebraic closure of Q. This is less of the fact that Q is a field is obvious. This is a little exercise, which is non-trivial, let's say. And so whenever you have a field, you can consider a certain group attached to this field. And so the group in question will be the group of automorphisms of the field Q bar. So what does this mean, the group of automorphism of a field? It means that it is the set of bijections from Q bar to itself, which preserve the field structure of Q bar. So this means that is the set of permutation from Q bar to Q bar, which preserve addition and multiplication basically, and send one to one. And so the group G is called the absolute Galois group of Q. And so this group G is exactly the central object studied by algebraic number theory. So people are very interested in understanding this group G, which is a very complicated group. And how is it related to algebraic numbers and algebraic equations? So if you give yourself a fixed algebraic equation, the group G will act on the solutions of this given algebraic equation. So I have an algebraic equation, I have Z a solution, I have sigma an element of G. Sigma of Z will be, sigma of Z will be again a solution of the same algebraic equation. So in fact, the group G acts, maybe I will put this here, on the set of any given algebraic equation by a finite quotient. So in fact, it's not the group G which will act, but a finite quotient of G which will act on an algebraic equation which is given. And so this was understood by the French mathematician Galois, which developed Galois theory. And as an application, he could prove that, remember this algebraic equation that I gave you before, is not solvable by radicals. So what does this mean for an equation to be solvable by radicals? It means I start with the coefficients of the equation, and I can express the solutions by either doing basic operations on the coefficients, such as addition, subtraction, multiplication, division, and also extracting nth root, for example, square root, cubic root, quintic root. You can always do this inside C because C is algebraically closed. So it means that somehow the solutions have a closed form in terms of the coefficients, but not all equations verify this property. Is true for equations of degree 1, 2, 3, 4, and it becomes wrong for degree 5 on. So this is an example of such an equation. And so in fact, the reason, the group theoretic reason behind this fact is that you know this group G which acts on the solution of this equation. It will act by a finite quotient, which in this case will be the group S5, or isomorphic to the group S5. So here, this equation have 5 distinct solutions. 3 of them are real numbers, and 2 of them are conjugate complex numbers, which are not real. And this implies you can also check that this polynomial here is irreducible over Q because, for example, it's irreducible mod 3. All of this implies that the finite quotient of G acting on this solutions of this equation is S5, and S5 is not a solvable group. And Galois proved that an algebraic equation is solvable if and only if the Galois group attached to this equation is solvable. So that's why this one is not. Okay, so this is a old result, 19th century. So let me move on to slightly more modern results. So I want to introduce what is called p-adic numbers. But first of all, because p-adic numbers are quite similar in some sense to real numbers, I will recall the definition of real numbers to start with. So the field Q is contained as a dense subfield in the bigger field R. In fact, R is the completion of Q for the Archimedean absolute value. And so R is indeed bigger than Q. For example, this square root of 2 is not a rational number. The same goes here for pi. And of course, rational numbers are real numbers, as you know. And they are all given by decimal expansions, which might be infinite. For example, this is an infinite decimal expansion of a rational number, which is 1/3. Okay. So what's the general form of a real number? You can always think of it as a decimal expansion. So a decimal expansion is a possibly infinite sum of this form, where the AKs are between 0 and 9. And I remind you that this decimal expansion is not necessarily unique. In some exceptional case, you can have two numbers which have the same decimal expansion. For example, one can be written 0.99999, etc. Or it can be written as a 1.000 finite expansion. Okay. So what is the P here in p-adic numbers? It's a prime number. So I remind you that a number is prime if it is an integer which is at least equal to 2 and which is divisible only by itself and by 1. So these are prime numbers. You can see that there are some big prime numbers, and these are non-prime numbers because they can be written as non-trivial products. And the fact that there are big prime numbers is not a surprise because there's a very basic theorem about prime numbers, which says that there are infinitely many of them. Okay, so now I have fixed my prime number, and I want to make an analogy between real numbers and p-adic numbers. So the field Q for my fixed prime P is contained also as a dense subfield in some field QP, which will be the completion of Q with respect to the p-adic absolute value, with respect to the p-adic norm. So very explicitly, how can I write an element in QP, which is called a p-adic number? I can write it formally as a possibly infinite sum of the following form. So it's the same form as real numbers, but instead of having negative powers of 10 here, you have positive powers of p, where the AKs, instead of being between 0 and 9, they are between 0 and p minus 1. So you might argue here, obviously, this sum is divergent because p to the k tends to infinity. But of course, it's not the case because you're considering a completion of Q with respect to the p-adic norm. And for the p-adic norm, p to the k tends to 0. So the topology on QP is very different from the topology on R. R is a connected field, and QP is totally disconnected. So let me just give you one example. So of course, QP contains Q. So any rational number has a p-adic expansion. And so, for example, this one divided by 1 minus p. As you probably guess, because of this geometric series property, and because p to the k tends to 0, the p-adic expansion of this rational number is this one, infinite sum. Okay, so let me give you a slightly more recent result than that of Galway on the previous slide. is a general principle, in fact, in algebraic number theory. In many cases, to understand properties of Q, or more generally properties of number fields, you need to understand properties of all the completions of the number fields. So here for Q, it means that you want to study Q, you study it as a subfield of R and of all QP together somehow. So let me give you an example of this local global principle. This is called local global principle. So suppose that you have a quadratic equation in n variables. So say it's of this form. Okay, I always put it under this form in any case. So obviously this equation has a trivial solution, which is all xi equal to 0. And so you're interested about the non-zero solution. So first of all, you want the AI to be rational numbers. The AIs have are in Q. And you're looking for non-zero solutions inside Q to the n. So theorem of Hassan and Minkowski tells you that this equation has solutions which are non-zero in Q to the n. If and only if this is the case inside R to the n and inside all QP to the n for all prime numbers. And because there's more room inside R and QP, it's easier to find solutions inside R to the n and QP to the n. And whenever you know that for R and QP you have a solution, then you deduce that you have a non-zero solution inside Q to the n. So this is the one instance of the so-called local global principle, and which is one of the reasons why you introduce p-adic fields. Okay, so now I will move on to even more recent topics, and I will talk about L functions, and more precisely those defined by Artin, which are called Artin L functions. So the most basic example of such a function is the Riemann zeta function. So the definition is this one. Zeta of S is the following sum. So this sum here, so what is S? First of all, S is a complex variable. This sum here will be absolutely convergent in some right half plane of the complex plane. And then it will admit, it will define a holomorphic function there, which will admit meromorphic continuation to the full complex plane. So this is the Riemann zeta function, which is meromorphic on the full complex plane, and which has also another very interesting description, which is the following Euler product. So this Euler product makes sense for real part of S sufficiently big, and then you extend meromorphically. So you do the product over all prime numbers P of these quantities, 1 minus P to the minus S, the inverse of this. And so you have two different expressions. The first one is a Dirichlet series, and the second one is an Euler product of the Riemann zeta function. And there are, of course, very famous and unproved conjectures about this function. And so Artin decided to give a possible generalization of this Riemann zeta function. And he attached L functions to Galois representations. So you remember you have your Galois group G, which is the absolute Galois group of Q, the automorphism group of Q bar. And so now I will introduce a bit about representation theory. So you take V complex vector space of finite dimension. And you call, so here G is the absolute Galois group of Q. And you call rho a representation of G on V if rho is a continuous homomorphism from G to GL of V. So the group G, in fact, is equipped with some topology, which makes it a profinite group. so in particular a compact group. And to say that you have a complex continuous representation of G on V implies that this representation in fact factors through a finite quotient of G. So in fact, you're somehow only considering, given your fixed representation, a representation of a finite group, finite quotient of G. And you call this a Galois representation. So now for each prime P, there's a subgroup GP of G. So what is the subgroup GP of G? In fact, is the absolute Galois group of QP bar. Remember, you have your field QP of p-adic numbers. You can consider a fixed algebraic closure QP bar. And you can consider the group of automorphisms of QP bar, which are QP linear. And that's the definition of GP. And there's somehow a canonical injection of GP inside G. So you can always see GP as a subgroup of G, okay? So once you know this, that you can identify GP canonically to a subgroup of G, then you can restrict your representation rho of G to GP. So this gives you a representation of GP on the same vector space V here, okay? And this is called a local Galois representation. So for each prime P, you have rho P, a local Galois representation attached to rho. So now I will not give the full definition of Artin-L functions because I would need to introduce some structure theory of GP, ramification theory, etc. This I don't want to do, but I can give a rough description. So the definition of Artin of the L function attached to rho. So it depends on, it is attached to rho, and it depends again on a complex parameter S. Is the product on all primes. So at the moment, my definition is purely formal, of some local L functions attached to the local representations rho P. And they have a shape very similar to this one. So more precisely, the local L function are the inverse of a polynomial in P to the minus S. So here the polynomial is 1 minus X, the constant term of which is equal to 1. Okay, so the definition which is involved is the precise definition of this local polynomial, and I will not give it, but roughly an Artin-L function is defined as an infinite product which is convergent in some right half plane of the complex plane. And in fact, Artin was able to prove, it's a non-trivial result at all, that LS of rho is a meromorphic function, just like the Riemann zeta function. Moreover, he was able to, he was not able, but he conjectured the following result, which is that if rho is an irreducible representation, and if the dimension of V is at least equal to 2, then the Artin-L function LS of rho is holomorphic. And this is an open, this is a very difficult conjecture, which is still open. Maybe I'll say a quick word about being irreducible. So you have your group G acting on your vector space V, and the fact that rho is irreducible means that the stable subspaces inside V under the action of G are only 0 and V itself, which are obviously stable. So suppose you have an irreducible representation of a dimension at least equal to 2, then LS of rho should be holomorphic. Of course, if the dimension is 1, this is not true, because in fact, if I go back to the previous slide, if I take rho, the trivial character of G, the trivial representation of G on DL of C, I get the Riemann zeta function, which has poles. So you need this assumption on the dimension of your Galois representation. And so this conjecture motivated somehow the Langlands program. So much later, Langlands proposed a strategy to attack the above conjecture, but he basically he made even more difficult conjectures somehow. So I don't know, you could argue, yeah, you want to prove a conjecture, you make more difficult conjectures, but it gives you insight somehow. So he made very, very general conjectures, which I will not state precisely. They're too complicated to state here. But some parts of the conjectures are now known, especially the local parts. They are known for all classical groups, more or less, and especially for GLN. So here is a very small but fundamental part of these conjectures. So you fix a prime P. So it's the local conjectures of Langlands for GLN. And the Langlands conjecture for GLN states that there should be an injection called LLC, local Langlands correspondence, from the set of n-dimensional representations of my local Galois group GP. Remember, GP is inside G, is the absolute Galois group of QP. So I have n-dimensional representation with a fixed n of my Galois group. So there should be an injection of this set of representations to the set of the so-called smooth irreducible representation of GLN of QP. So you see here, n is the dimension of my local Galois representation of GP. And here, n appears in GLN of QP. So there should, to say that there's an injection between two sets is not interesting very much. It's just a matter of cardinality. So of course, you want it to be a very clever injection satisfying a long list of properties, which I can't state. Let me say a word about what the smooth irreducible representation of GLN of QP is. It's just a representation of, so first of all, GLN of QP is the group of invertible matrices with coefficients in QP. So it is a group. A representation of a group is a linear action of this group on a complex vector space. And to say that it is smooth, in fact, means continuous. It's the same thing. You have some topology on a GLN of QP inherited from that on QP, which is very strange. And you're looking at continuous representations of this group on vector spaces. And so the thing is that smooth irreducible representations, as opposed to Galois representations, are most of the time infinite dimensional. The only ones which are not infinite dimensional for GLN of QP are those of dimension 1. All the others are infinite dimensional, though they are still irreducible. So the LLC claims an injection between these two sets, satisfying a long list of properties. And it is now a theorem. It has been a theorem for a bit more than 20 years now, due to the mathematician Harris and Taylor, and also Guy Egnard, which very quickly after them gave a simpler proof of the existence of this local Langlands correspondence. Okay, so I think I will finish this talk, so probably in advance by talking about a result of mine in the field. So it's about local exterior square L functions. So maybe as I have time, I can say a word about the list of desiderata that you want the LLC to satisfy. On both sides of the correspondence, you can define, for example, L functions. So here to a local representation of GP, you can attach the local Artin L function, which I did not really define, but if I go back to the previous slide, this is the local Artin L function, you see here. And on the other hand, the mathematicians Godman and Jacquet define attached to any smooth irreducible representation of a GLN of QP, another type of L function called the standard L function. And so one of the properties that you expect from this correspondent LSC is that it preserves L functions on both sides of the correspondence. You have L functions attached to one object rho on the left and another object pi, which is LLC of rho on the right. You want those L functions to be equal. This is one of the requirements that you want to put on LLC. If the list is long enough, this injection LLC becomes unique. And this is a result of this mathematician here, Guienia. Okay, so let me give you an example of one of one of the type of results that I proved a while ago. So you take a rho p VP representation of dimension n of GP. So GP is the absolute Galois group of QP. So you have a finite dimensional representation of this group. So it means that rho p is a homomorphism from GP to GL of GP, right? If you have such a representation, you can build a new representation of GP called its exterior square, which I denote like this, exterior square of rho p. So the definition is not too complicated. First of all, it's a representation of a dimension n minus 1 over 2. So here I start with a representation of dimension n. I obtain a new representation of dimension n minus 1 over 2. So the group GP acts on VP, so it acts diagonally on the tensor product VP or times VP. Okay, on this tensor product, you have diagonal action of GP. And for this section, you have a stable subspace inside the tensor product, which is the subspace generated by the differences of the following form: VW minus WV. This is a stable subspace. And so from this representation, I get a new representation on this subspace. Okay. So this is the exterior square of a Galois representation. So you get a new representation of GP, and in particular, you get a new local Artin L function attached to this new local representation. Now, because I will use the local Langlois correspondence, you remember to rho p, the LLC of rho p will be a smooth irreducible representation of GLN of QP. Okay, so you take such a representation, and a while ago in the 1990s, the mathematician Bump and Friedberg, the work of which I extended somehow, attached a local L function to the representation pi p. So again, I will skip the details, but they attach it by a method which is called the Rankin-Salberg method. So whenever you have such a representation pi p, smooth irreducible of GLN of QP, you can realize it on the space. So as I said, these representations, smooth irreducible, are in general of infinite dimension. And you can realize this representation pi p as a space of functions on GLN of QP, from GLN of QP to C, which are called Whittaker functions. You obtain the so-called Whittaker model of pi p. And then you have so you have functions on the group GLN of QP, and you can integrate these functions on GLN of QP, or more precisely on some subgroups of GLN of QP. And you can integrate them against some quantity depending on a complex parameter. So you have this kind of integrals which depend on a vector in the space of pi p, which is a Whittaker function, and they also depend on a complex parameter, and they turn out to be algebraic, or more precisely rational functions in the parameter p to the minus s. And in fact, it makes sense for these integrals because now they're algebraic objects which live in some kind of ring, in fact, or more precisely in the fractional ideal of some Laurent polynomial ring to define the GCD. And this will be somehow the definition of the local L function here attached to pi p. It will be some kind of GCD of Rankin-Salberg integrals attached to Whittaker functions on GLN of QP inside the Whittaker model of pi p. But in any case, it's very analytic process, but which turns out to be algebraic in the end and to define an Euler factor like this, which is the inverse of a polynomial in p to the minus s. And so here is what I proved in 2015. So you take rho p local Galois representation. You define pi p to be the smooth irreducible representation of GLN of QP, which corresponds to rho p via the local Langlands correspondence, which, as I remind you, exists by the results of Harris, Taylor, and Enya. And then what I proved is that the Artin L function, remember the Artin L function attached to the local Artin L function attached to this local representation here, the exterior square of rho p, is exactly equal to the Bumfriedberg exterior square function attached to the representation pi p. And so why is such a result useful, such an equality? There are two objects defined in completely different manners. And because this one is defined via the Rankin-Salberg method, so it's defined via integrals depending on a complex parameter, you understand these integrals quite well, and somehow you understand the poles of this local L function very well, whereas the poles of this L function could be quite mysterious somehow. And so this gives you, this type of equality gives you good analytic properties of the L functions on the left, which are difficult to obtain if you don't have such equalities at hand. In fact, for example, I'll just say one last thing to say that this L function has a pole at 0 means that the representation pi p admits a local period to some Levy subgroup of GLN of QP. So it's related to the theory of periods in the theory of automorphic forms. And yeah, so I apologize. I've been probably too quick, but this is the end of my talk, and I thank you for your attention.
Okay, thank you, Nadir. Thank you very much for very deep talk, I would say, because it started with a simple definition, but it went to very complex structures toward the end. Okay, there are a few questions in the chat. Firstly, let's take those. Okay, the first question is about the Artin conjecture. So what was the motivation Artin here when he was posing this conjecture?
Yeah, so the truth is that I have no idea. I guess it might either be examples or maybe he had some geometric motivations in mind, but yeah, this is beyond my culture. So sorry, I can't really answer this question.
And in this same conjecture, so there's another question. So by finite dimension, you mean the dimension
greater or equal to, yeah, greater or equal to 2. Yeah.
Okay. One more thing regarding to this conjecture, is there any restriction on the field? So field of the vector space V?
No, so here V is over the field of complex numbers. So it's always complex numbers. But the definition of Artin L functions, you see here, rho is a representation of G, the absolute Galois group of Q.
Mm-hmm.
But it could be the absolute Galois group of any number field. Mm-hmm. And you still have the same Artin conjecture. So where you can replace the field is more, this is the absolute Galois group of Q. It could be the absolute Galois group of any number field. And I recall you that the number field is a finite extension.
Okay, and what about this GL of V, absolute Galois? So is it unique regarding to every Galois group? I don't think.
No, so an ordinal function is attached to a fixed representation of G. Okay, so it's LS of rho for a given rho. And what is when you fix a representation of G, it means you fix a complex vector space of finite dimension V, and you fix a homomorphism from G to GL of V, a fixed group homomorphism.
And what is the systematic way to move from the Galois representation to local Galois representation?
So okay, yeah, this I was not very precise. The systematic way is just by restricting. So you see, I have a group
by tensoring the map.
Not really tensoring. You see, you have a map from G to GL of V, and you have a subgroup GP of G. You just restrict the map. It's very naive, just naive restriction of a map. The subtlety. Yeah, sorry. Let me just say because this is interesting. It's not clear at all that this group here is a subgroup of G, but you can also see GP as the automorphisms of Q bar, which are continuous with respect to the p-adic topology somehow. So this is a more explicit description as a subgroup.
Okay, and one more thing, if you go to the slide of your last slide, local exterior scale function. Okay, I do not get this group action. Okay, this GP is acting on which set? So
VP. So the GP is acting on VP, right? It's you have a linear action initially, rho P, which is an action of GP on VP. So now on the tensor product, you have a natural action of GP times GP. Okay, if I take an elementary tensor V1 O times V2, I will have G1 V1 O times G2 V2. This gives me a group action of GP times GP on the tensor product. But then I see GP as the diagonal of GP times GP. And this gives me a group action of GP on this tensor product. Basically, it sends VW to GW, okay? GV.
So this exterior product is becoming the diagonal of this tensor.
So at the moment, this is the tensor product, but then the exterior product can be seen as a this stable subspace. The stable subspace they're generated by these differences. For example, suppose you have a E1, E2, En as a basis of VP O times VP. This vector space will have as a basis EI, EJ minus EJ, EI for I smaller than J.
Okay. And the last question which I have is there some way, systematic way of constructing these meromorphic functions? These are very special functions.
So there is no precise definition of L function. There are many ways of defining them. There are geometric ways, which I don't know very much. And in the Langlands program, essentially, there are two methods, two or three methods. Let's say, two methods. One is a method which was initially defined by Langlands, which is called the Langlands-Shahidi method, which I didn't talk about. And the other one is the one I was suggesting, which is the Rankin-Salberg method, which is to define L functions through integrals depending on a complex parameter. These are the two main methods, but they don't produce, as far as I know at the moment, all the L functions of interest on the Galois side. They produce many of them, but not all of them.
And what do you mean by of interest of the Galois type? What does it mean?
So you see to each RTNL function attached to a local representation rho P or to a global representation rho, but of the Galois group, you have an RTNL function attached to it, okay? And so you would expect that on the representation theoretic side of GLN of QP, you should be able to define the corresponding L function using one of these methods, the Langlands-Shahidi method or the Rankin-Salberg method. But at the moment, using these methods, we don't get all RTNL functions attached to Galois representations. Not,
And these finding these function give assertion to that conjecture, Artin conjecture.
Yes. You are absolutely right. Such type of equalities, but say not such type of equalities in the global case, say they every time you have one, most of the time you can make progress on the Artin conjecture in the special case to consider. Yes, absolutely.
And one thing I was a bit curious. Please excuse my naiveness in this area. What is the role of that p-adic norm is playing in this whole build-up?
Can
that p-adic valuation, the p-adic valuation you define when you are defining the p-adic numbers.
No, it's just that first of all, you mean the role in
these constructions.
In these constructions is that your L functions on the Galois side are defined as Euler products, and so and the Euler product and the Euler factors depend on
the
QP, because they depend on the absolute Galois group of QP. Yes.
Yeah. Thank you. Hania, can you speak your question yourself now? You are unmute. You can unmute yourself. Hania?
Yeah.
Go ahead.
Thank you for this very nice talk. Number theory is something which is beyond me. So yeah, I really enjoyed it because you started out being very down to earth. I just wanted to know about the program. So just to know, it offers a bridge between number theory and let's say geometry. So as is the case usually with these bridges, one side informs the other. As it stands with those long list of correspondences that are conjectured, which side is informed more than the other? Is it which side does it serve better?
Yeah, sure. So that's a very interesting question. First of all, let me make a first remark. What I talked about is more a bridge between number theory and representation theory. So, but there are two aspects in the Langlands program. You have a bridge between number theory and geometry, which I'm not at all an expert of. And you have a bridge between number theory and representation theory. But in both cases, people are looking for number theoretic information, either through geometric methods or through representation theoretic methods. So it's geometry which would give information on number theory. At least that's how you think of the people who do this kind of stuff, which I'm not, deduce number theoretic information from geometry. But for example, the LLC is proved using a geometric method. Somehow you have your two groups, GP and GLN of QP. You construct some geometric space on which you have an action of GP and GLN of QP, such that both actions commute. And then this is a geometric space which has some cohomology spaces attached to it, which gives you representations of both GP and GLN of QP. And it's using this space and its cohomology spaces, which allow one to prove the local long-length correspondence. So the local long-length correspondence for GL and QP is very geometric, whereas for a classical group, it is much more analytic and representation theoretic. You deduce it from GL and of QP somehow for classical groups by using the so-called trace formula.
Right. Thanks. Thank you.
Thank you. And Nadir, what about the other side of harmonic analysis with the connection with this L function and these kind of theories in the Langland book?
So that's also a good question. So the harmonic analysis is done not on the Galois group. Galois group is not very interesting. It's it's very interesting, but it's a profinite group, so it's compact. Whereas those groups, GLN of QP, are reductive groups. Not all of them are compact. And in particular, whenever you have a reductive group, like a GLN of QP, over a p-adic field, over a local field in general, you can study functions on this group, smooth functions or a more special type of functions on this group, Harish-Chandra. Let's say smooth functions with compact support. The very good space to do harmonic analysis is a space defined by Harish-Chandra. And you have a so-called Harish-Chandra Plancherel formula for these groups, which is a generalization of the Plancherel formula on R, for example, or difficult generalization. And so you also have a Plancherel measure, and you have a very explicit Plancherel formula for these groups, which give a description of a very explicit Plancherel measure, which depends somehow on some complex parameters. And you see those L functions appearing in the Plancherel measure of your group when you do those very explicit Harish-Chandra Plancherel formula. So this is how they appear.
And again, our ambitious question, sort of. Does it has any connection with the p-adic geometry what Peter Scholz introduced?
So say it again, with the p-adic what?
P-adic geometry, which was introduced by Peter Scholz.
Yes. Of course, he introduced. So, but this I don't know very much. But he's of course a very brilliant mathematician. Who introduced new geometric objects called perfectoids, and is way beyond my culture. But together with a French mathematician recently, they were able to define a map which should be some kind of semi-simplification of the local non-length correspondence for any reductive group using this arithmetic p-adic geometry, as you mentioned. So it's not the exact local long-length correspondence, but it should be a semi-simplification of it.
That's it. Any other question? If someone has any question, you can raise your hand, or any comments you would like to share. Okay. If this is the case, let us thank Nadir. Nadir, it is always so excited to have you here, and
yes.
This is always quite rewarding to get the connections of algebraic numbers and playing with the representation, with geometry, with analysis, a lot of things in one complete package. Everyone can find its own interest.
Yes, and I see Hamza and Aksa, which I met at SMS back in the days, saying thank you. So I salute them, and everyone that I met before. And I was very happy to give this talk. I I apologize for it to be slightly short, but gave more space to questions. I guess it's fine.
No, I think this is not short. in the prospect of the spectrum you have opened up, this is already too much for the audience. I think you have done a remarkable job. You started with a very basic definition, which was very good to keep everyone intact, and you have done a remarkable job. Thank you very much for a wonderful talk. Thank you, everyone,
Thank you.
for your appearance, and hope to have more talks from Nadir in upcoming years, or maybe in this year.
My pleasure. Yeah, sure.
And moreover, there is a small announcement that we are going to suspend this John Conway series for a while, for the half month of March, because we are going to have the SIMPA school, which is going to start from the March 1st to March 11. So this is highly intensive activity we are having here. And during that time, there will be no John Conway, but we will resume soon. And with a very big seminar that is dedicated to the 60th birthday of Bernard Strumfels, who is current the director of Max Planck Institute, not Max Planck, Max Planck Institute. And moreover, he has a joint appointment in University of Berkeley. So he will be talking about some recently developed connection between algebraic geometry and partial differential equations. His recent paper on arXiv. Once again, thank you very much, Nadir, for a wonderful talk.
Thank you very much.
And thank you, everyone. That's all for today.
Okay. Thank you. Bye-bye.
Thank you. Bye-bye. Take care.
You too.